chat, whatever
Okay.
you want to. Okay.
Yeah, that's fine. All right, so I think we're live. Can everybody hear me? I think we should be good. Okay. All right. So this breakout session is basically what we have found works to teach geometric tolerancing to machining students. We have really been trying to implement this throughout, the entire program. It has been, with trial and error, see how things go. We've had a few years of this now, but the main goal of this is how to teach this topic to machining students, right? So if I continue here, I have a slideshow. All right, a little about me. I work at the Hudson Valley in the new CAMS building. I've been here since 2009. I started here full-time in 2015. And I teach all the machine shop courses, among other instructors. And I also teach the metrology course mainly, all right? If you want to get hold of me on email, there's my email address. If you have any questions or anything after this, you want to get hold of me, I'm always willing to talk about, how to implement this better and other topics as well, anything machining related. My YouTube channel is ITD Machinist, all right? There's some content on there, mostly machining content. One thing I forgot to add is one of our other instructors has an excellent YouTube channel. He's our local engineer, I guess you could say. His YouTube channel is R. Dean Odell, and he puts a lot of effort, especially with COVID changes. That's why both of us ended up getting a YouTube channel. COVID really pushed us online for many courses, so we had a lot of video editing experience, especially Dean. He's really big with that. So some of the goals that we really wanted to achieve, and all these goals were based on not only our experiences in industry as instructors, but from our advisory board, and just again, even a lot of us work in industry over the summer, and we see the changes and what's required just by the drawings coming in. All right, we want graduates that can make and spec parts correctly, to have geometric tolerancing on them, period. No gray areas, or as little gray areas as possible. We want them to hit the shop floor and make components, within reason for their employers. We tell a lot of our advisory board members that, if you don't have Haas machines, which we all have Haas machines, if you don't have Zeiss coordinate measuring machines, there's going to be some training involved. But overall, if you have Haas machines, if you have Zeiss coordinate measuring machines, they should be able to know how to run these and make components for you. And if the components have GD&T, it shouldn't be a problem. That's our goal. All right. Are we there? About 50-50. It depends. We are still changing as time goes on. We want to make sure they can reference the standard for any decisions made during the manufacturer inspection process. The big thing here is, if somebody's questioning what they're doing, we want them to be able to cite the information properly. We kind of want to avoid them citing a textbook. We would be better to cite whatever standard they have. So we use the 2018 standard, but if they're using 82, 94, 09, whatever, we want them to make sure that they know where to find that information and, defend their decision, or look up information to, support something that they want to do, or this is the way this is interpreted, this is the way I want to make it or fixture it, etc. We want to get away from the hobbyist drawings. We want to get away from, if you look at any model building drawings, anything like that, things that, don't have tolerances, or things that may say, this is a close fit. What does that mean? We want to have our drawings be as industry standard as we possibly can. All right. We want to increase their confidence. We want to make sure they have the tools they need to understand these drawings, and that they look at the drawing and not be totally confused. Again, we're not talking about, very difficult components, a lot of geometry. You'll see some of the drawings later. They're not, some of our projects are fairly simple, but we will tolerance them. We'll add different kind of, I don't want to say traps, but different areas to raise questions and to look things up that are unnecessary for the actual function of the workpiece, but may matter to get a skill taught to them. All right. And again, take the fear away. It's amazing. A lot of the question, geometric tolerancing, a lot of people hear that and they kind of, at least locally, they get flustered. From a machining standpoint, if the drawing is done correctly to the standard, it does, in my opinion, make it easier, especially to fixture and to inspect and to update if there's an error. If you have to calculate bonus tolerance and work with that, it's really not a big deal. So we want to take away the fear, and that is a main issue. Why is it so important? It's everywhere. All right. One of the big things I noticed is that there was a GD, we had a drafting program here at one point, and geometric tolerancing was required for them, but not for the machining students. And I was always kind of surprised at that. It's not just for engineers. It's not just for draftsmen. It's for everybody in the shop. Everybody's got to be on the same page. I see that when I go out in industry. A lot of people have the engineers maybe take a training class and they're implementing it. And then the people on the floor, they have not had the training and they don't know how to inspect to it. They don't understand. And there's a gray area, and then you have issues. So we want the machinists, the people making the parts, or the inspectors inspecting the parts, totally fluent in this as much as we can in our time frame. We understand that they're not going to be senior certified, but we would like to see them, again, be successful in this and at least be willing to take the next step when they get out there. So from my experience, the traditional GD&T education is very lecture intense. It's boring. I was teaching a class last week, and the first thing I tell people is this can be dry, especially getting through the first the set of rules. The first day of training is usually pretty dry. When I took this course, it was a 5-hour lecture every Friday morning, and the attrition rate was like 80%. It was worth it at the end when everything was kind of put together, but to get past that, it's hard. A lot of students say, why do I need this? That is one of the things brought up. And you'll see some of our decisions later on. We went a certain way because of this. They'll say, well, why do you need this? Why are we doing this? Where I work, they don't have these drawings. They're coming down the line. The more time goes on, the more this is being it's everywhere now. I've seen drawings that aren't really high-end components. They have it. True position is the big one. True position people use a lot. The courses that I've taken, they were all electives. They were not geared for somebody making or inspecting the parts necessarily. Even the instructor came from an engineering background, and although they knew what they wanted, they knew how to tolerance it. They did their stack ups. They just didn't necessarily know how to fixture it. They didn't know how to inspect it. They didn't know what to cut first. They didn't do this as a machinist would want to see it, or the information that pertains to somebody actually manufacturing the workpiece. And that is where we really strive to show these students, what do you need to know, how to interpret it, how to communicate with the engineer, and really get the part done correctly and use all the tolerance. All right. So what we found, and we implemented this in the last 2 years or so. GD&T starts early. It's become where it used to be, well, here's coordinate, you work with, coordinate tolerancing for a while. And then this geometric tolerancing comes in and, well, why are we doing this? Why don't you just do plus or minus 5? All this type of issues we've had. And we've found that if you start it from the beginning, and we're not saying tight tolerances necessarily, we're saying that the talk and the feature control frames and the Datum system are all there from the first project they make. And the parts are simple and the geometry is simple. And that really helps, instead of having complicated geometry and complicated coordinate systems and complicated geometric controls, start on simple geometry with loose tolerances and talk about it and get the talk going. And we hit on this in labs first. And we have found that it is much easier for the print reading instructors to have their more dry lectures on it when they have a reason to learn it. So that goes into the next bullet point here, is covered in multiple classes. It's everywhere. It's not like if I make it through geometric tolerancing, I'll never see it again. It's, well, you got to learn this, and we try. It's difficult, but we try to sync up the classes to cover this topic. So something that is practiced in lab, let's say they have a lot of questions and they're busy making their parts, and we go over it and they have some inspection questions. The next class, they'll have a lecture on a specific topic. Then they'll come back, and we come back to the inspection. They'll have a better understanding of why we're doing something, and they'll have a lot of the theory, and it seems to work. Again, we are always updating this to try to make this work as best as we can, but this has definitely worked. We've had great student success with that topic, with that method. The redundancy is big. I know it may sound dry, but we have found that with this topic, you have to say it multiple times. And I've done this with to engineering students where I'm doing more of a lecture style class. You have to repeat yourself because some of it is very wordy and some things follow into one another. So you have to make sure there's redundancy, not so much necessarily in your lectures, in our case for machining students, but what I said previously, where you want them to see it in lab, where they have to make the part in spec, but then they also have to have that experience go with print reading, go with specifically when you're learning the Calypso software for the Zeiss, it has to link together. And that has definitely been successful. Okay. Now we do cover coordinate tolerancing. It's not abandoned. That's one thing that we stress on, is that basic, coordinate tolerancing is not just gone. We have a lot of drawings that have both, and we cover at the same time, and they're treated as equals in a way. And I know that they're not necessarily equal in what they do, but they're just treated as, this is a drawing, we need to work with it. We don't look at it as if it's special, and that has helped with the Y situation. It's not unique, it's not special. This is the way it is, and this is how to successfully navigate this. Okay. Now, when it comes to actual tolerancing, we'll get into zero MMC, true position, different profile of surfaces. The tolerances are appropriate for the machining operations being taught. So that means that we're not going to throw very tight tolerances, very complex geometry at a first semester student. We will space that out, and as the projects get more difficult, we might tighten up a tolerance to force them to do a certain machining operation, things like that. So we do tailor this to make the best of it for every class situation. All right. The other thing we've started doing is all student projects are fully inspected by the instructors. So we grade them based on their ability to hold the tolerances. We're very strict on that. We grade them on, the overall look of the workpiece. Paperwork is very big, making sure they're honest, making sure that's, being inspected properly. We still use a plate, but we have coordinate measuring machines, and we will program them and run the students' parts just as we would in industry. We are trying to align our 2 years here as much as industry, as much like being as work as possible. And it seems to work. It helps the faculty. I'm not going to lie. It helps the faculty keep current. It helps faculty see, well, this geometry, this didn't achieve what I wanted to in the machining lab. We might tighten the tolerance, loosen the tolerance, change the geometry a little bit to get what we want. And the GD&T just tolerances it. Okay. On the flip side, we might want them to do profile of a line instead of profile of a surface, and we can update that depending on where they are in their coursework. All right. Deadlines are critical. I know that's off topic for the GD&T standpoint, but we found that holding students to deadlines, it by far helps them in their education because they just get further behind. So when it comes to our grading system, the deadlines, and that includes inspection, are very critical. And we have open lab times and things to help them with that. So some of our drawings, let's see if I can get these over here and I'll show you this. I have a few here. Let's see what we got. There's one. So this is just a dead center. And you can see that Dean Odell does an excellent job with his drawings. You'll see that we try to make them as nice and industry standard, as clean as possible. This links up also with our CAD class. The CAD class, they will make drawings like this. We don't do it quite like an engineer. We wouldn't spend, it's a 3-hour class. They make very nice drawings, but they're not advanced assembly drawings or engines or anything like that. But they're expected to make drawings like this and understand the basics of tolerance stack up and where tolerances come from. From a machining standpoint, they have to make this, and we go over order of operations, what to do to what, how to create the datum references, how to inspect it as you go. We can talk about custom gauging depending on the part, but a lot of times we try to show them with V blocks, column blocks, 1, 2, 3 blocks, height gauges, all that type of stuff as much as possible, with the understanding that a lot of shops aren't going to make custom gauging for one part, especially in the job shop environment. They're not going to do it. When it comes to the coordinate measuring machine, this would be fully inspected. Right? We have all different ranges of tooling. This example is sort of interesting. One thing I always point out, and I am drawing on the screen here. When you got a thread spec, when we show them, you know, technically that's the pitch diameter, and it would be nice if the engineer went to minor and they could put the note here. And that's a conversation that comes up in print reading, and why you can do that. Can you get away with it? What it means, because to the engineer, it may not matter, but to the machining operation, to check to the pitch diameter can be tricky. Okay, so that's just one example. We talk about in this application, you know, this is true position versus, if, you know, it could be run out, the total run out, circular run out. Why, you know, why is this true position? Why is this run out from a design standpoint? Okay, so these are things that, you know, we really focus on, and, you know, we'll go from R30 max and we'll start to tolerance that at like plus or minus, and they can see that if this is something that, let's say it's a range that doesn't match an insert, you know, radius that we have in stock, that we have to buy another insert, and why that makes a difference. And that's real important. It's not so much sometimes the big concepts, it's the little ones. All right. We also go through the revisions. I know that's not GD&T, but revisions are big. Make sure you pay attention to what revision you're on, how the same part can have multiple revisions. Sometimes they won't label the revisions, you know, like this and this. And then it's like, well, why didn't they label it? And that is a good example. And it really helps the students realize, well, this is why it needs to be labeled. Okay. We also have the specs up on the top and where the tolerances come from, where to look them up. Okay. So that's one example. Another example we have is, let's see, we got here. We do have a hammer here. I think it's this one. Okay, so this has been called the most expensive hammer ever, but a lot of the specs on here are mainly this is a lab 2 part. So this is an advanced project for them, and it's over tolerance for a hammer, but that's not the point. And a lot of the conversations that come up is, you know, why is this tight of tolerance? As a machinist, that's not necessarily the call you have to make unless you're in maybe a prototype environment. You know, you have to make the part. You're assuming that the part was quoted given the said tolerances, and you need to achieve that. So that the tolerances hopefully dictate the machining operations. All right. You know, you have the different alignments on this right here, over on the hammer handle here. And you have the A-C alignments, okay, and the composite control for profile of a surface and what that means and how to control it, and the thread specs, okay. And, you know, that has really helped us, because the big thing with a lot of the students, they say, well, what matters to what, and how does it measure to? And that really covers the Datum system very well. All right. Why are some tolerances basic? Why are some not? And that really helps. And that's all on purpose. Nothing on this necessarily, it needs to be as tight as it is. Okay. Other options we have here: profile of a surface all around except as noted. We grind form tools for these radii, and we have a form tool that I made for this radii for the students. You know, location of datum feature symbols here, whether it's on the mid plane or not, or the center axis in this case. All right. Let's see what else we got here. Got my mouse over here. All right. So the 3 parts of the hammer itself, and then the assembly drawing, all on one sheet. And they do get a size D drawing, a large drawing to work with. That's another thing we worried about. They get 8.5 by 11. They get 11 by 17. They get the larger size D size. So they get to work with different drawings. Cleanliness of the drawing, labeling of the drawing is critical. You know, try to overall, I don't want them handing this in all greasy and dirty. Things like that are also very important. Okay. Again, different datum call outs. But you see that these drawings, this is a hammer, and this is out of a very common, based on a very common hammer design that we've had. I don't remember if it's at one of the machining, I don't remember if it's out of a book, an older book, or if it's out of just prints we had around, like legacy drawings from from our program. But this little ball peen hammer, you know, we stepped it up with this one. The other thing is that, on another note, this hammer covers working with stainless steel. The hammer handle and cap are stainless steel. The head of the hammer is brass. So that is another thing we try to hit on, is making sure they work with different materials, and that's very important. Let's see what other drawings I have here. Here's another one. This is a lab 1 part. This is one of their first turning parts. So one of the first parts they make on the lathe. This is made of aluminum. And this is also one of the parts that's going to be one of the first parts they make in the CNC lathe. And that's one thing I wanted to bring up also, was linking up the manual shop to the CNC shop. So when we assign this part twice, that's not necessarily because we want two of them. That's because that if they make it manually and inspect it, the only variable to go to the CNC is the programming and setup on the CNC machine and what changes. So we're focusing on one aspect of it. The GD&T should be a refresher. This will be one of the first projects they make. So a lot of this part they should be used to doing, and it's a good, third semester September part to make. Right, very simple. Covers, boring, drilling, boring, outside turning, parting, aluminum, nice safe material. One of the nice things about this part that I really like is it covers profile of a surface, and it's in probably its simplest form, where it's just essentially, it's not one of the things that I always had an issue with when I was learning this was profile of a surface was treated as like only for advanced mold surfaces, and I got in industry and I'm like, that's not true. Simple depths and what that means and the tolerance zone to what, and also notice one thing that Mr. Odell is very big on is that he changes where the basic dimensions come from and how that changes where the surface needs to be inspected to based on the datum reference frame, or based on the feature control frame, sorry. All right. So these are some things, surface finishes we get into. All right, detail views, calculating bonus tolerance. I think one of these parts, if I remember correctly, has some 0 MMC. It might be the hammer. Yeah, right there. It's this one. Right there. So we cover that because 0 MMC is starting to become very common, at least in our area. Different scale factors. Sometimes. You're talking about scaling. I just got a question here. Do you do different scale factors on your prints for students? Sometimes, but not normally. Not normally. Usually, if they're not scaled 1-to-1, they'd be whatever size would appropriately fit the drawing to make it look clean. I'm assuming you're saying, is it covered like maybe like a Mylar drawing where you would, one of my other previous employers, they had drawings that had some dimensions, some tolerancing, but they were all drawn 1-to-1, and you would base a lot of things off of that. They're called Mylar prints. But not the scaling is not really into the, as far as the shop standpoint. Now in the actual CAD class and into the print reading course, yes, that's in there. All right. And they would actually make drawings to different scales depending on what size sheet they're working with. All right. Now the 0 MMC, the only reason that is covered big time now is because industry locally demands it. And the issue that a lot of what I see out there and what people have mentioned to me is that 0, it gives a lot of issues in the shop floor because they don't like to see that. So they don't really understand it. So we make sure we cover that, within the first year. The other thing is profile of a surface for more than it was traditionally used for. I'm curious to see what your feedback is on this, even if you email me after this. Profile of a surface is used way more than I've really seen it in the past, within the last 5 years. I'm not sure if it's a new engineering trend or they're really fully starting to understand it more, but we do a lot of profile of a surface, how to inspect it with, the coordinate measuring machine, which makes things nice, how to do some work with the comparators if you have to, and how to do it in the plate when you can. We try to avoid, we would talk about custom gauging if we have it, but any real advanced profile of a surface, complex geometry, that is left for when they get ready to do CMM inspection, and then then the parts they make can be inspected on the CMM. All right. And I think that's the only last one I want to cover before we finish the slideshow is this one. This is one of my favorite drawings that Dean Odell did. And this drawing is to help not only his class, but all the shop classes understand datum reference frames, because in our opinion, the datum reference frame, as from a machining standpoint, it's how to fixture it. It's how to fixture it between manufacturing and assembly. It's how it's supposed to be held, where these holes need to exist in the assembly based on whatever, what is sort of happening. So he has 4 different parts, 4 different datum reference schemes. I'll try to zoom out here so you can see this. Same part, different datum reference schemes and different ways to do it. So we do have this one around. This drawing that he did a great job with this. This one really helps the students out. For some reason, once we get past the datum system, and we get into to create the datums or then fixture to it, and 3-2-1 rule if they're planar and things like that. By that point in their education, that's a huge step. Machining students are always constraining the 6 degrees of freedom anyway. Okay, so when you bring it in wording, how to fixture something, and word it as if it's a datum reference, what you're constraining to what, in what way, that has been the ticket in my experience. I try to relate things to, if you're squaring the head in the milling machine, this controls your orientation. You indicate the vise, that would be like your 2 points of contact in datum B, that'd be your clocking, and then your orientation. And then you have 1 point of contact would be like a stop on the x-axis of the machine. And of course, the y-axis would be the solid jaw, and the z-axis constraints would be, the z on the machine, or whatever plane the spindle is perpendicular to. That has really helped us, that explanation, or a similar one. Trying to bring this to the machine tool, to hands-on technical students, and word it in a way that is hands-on, and showing them that's the key. We are evolving with that, but that avoiding the long lectures, that was key for us. All right, let's see what else we have here. Can you magnify that so we can see it? Yes. Let's take a look. Hopefully we're on the right drawing here. I'm getting these questions in, so bear with me. Something like that. That's one drawing. And so hopefully it looks okay from my side of it. But I know these drawings, when I was at RPI last week, I had to zoom in quite a bit to have them come in contrast. All right, so there's one of them. Another one. Again, it's just the same part, just a widget. It just has different datum reference frames, or different datum callouts. Another one, bottom right. And this one here. Okay. So I'll minimize this. Let's get back to the slideshow. I know I got to watch my time limit here, and I want to leave some room for questions and whatnot. All right. Key concepts. Talked about a lot of these already. Datum system, familiar with all geometric controls. What is bonus tolerance? How to calculate it, when you use it, what to do with it. True position's big. Inspecting the actual mating envelope, very important, what that means. Rule 1 boundaries, what to do with that. Profile of a surface, like I talked about. And when is it important to use coordinate tolerancing? We don't enforce, GD&T is not necessarily like the answer. You don't have to, it's not everything. It's used for fit form function. If it's something that is non-critical for fit form function, then coordinate tolerancing may be applicable, and you need to know how to work with both. All right. Talk about hands-on learning. All right. This is the key for us, and I'm really curious to see what everybody has to say. From a technical standpoint, we do get into all the. I know there was one question I'm looking at. We get into everything that is in the standard, and that's tough to cover, and even in a semester or 2 semesters, even 4 semesters, it's a lot. And we try to cover all the big points here, like datum shift and things. We talk about fixturing with it. We talk about the CMM, but we don't really get into the true details of it. We do in different terminologies, in the later standards, whether it's maximum material boundary versus maximum material condition, things like that. But the key to set them up with a foundation for learning this, maybe they go take a specific class from techies or something, or they need to work with it at work. The key to get rid of the fight or the fear is have them work with it like it's nothing special. It is the way it is. What does this mean? How do we inspect it? How do we fixture to it? That's been our experience. Okay. In CAD, Odell is very big with tolerance stack-ups, where they come from, why tolerances are what they are, why a tight tolerance does not guarantee a good part. The drawings they create, again, are not advanced assemblies, but they are to the standard. They're very clean. They're very clear to understand. And they do a good job of that. And we use SolidWorks for our CAD software. Our metrology course. We do cover a lot of surface plate setups for GD&T requirements, but that is also covered in lab. So we have a course called Advanced Dimensional Metrology. And that course, really, the focus there is the coordinate measure machine. So they learn Zeiss Calypso. And again, that's becoming more and more common, even if it were PC-DEMIS. CMM programmers, that is an option out of this degree path. So we really focus on that in there. That's not to say we don't cover basic inspection, surface plate work in other labs. They get a lot of surface plate time. Okay, and they cover, you know, whether it's geometric control or not. All right. We work with and again, this is not GD&T related, but when it comes to CMM programming, we cover not only with a model, but without a model. So what if you don't have a model? And that's been industry demand, because a couple of places I was working with, and they're like, we don't get models. They have them, we just don't get them. It's very difficult to get them. We have to work with no model. So we work with that, and then we work with how to put in your basic dimensions or your nominal dimensions. Okay, how to type in your specific tolerances if there's no model-based importing. I know on Calypso they call it like PMI or something like that, where it imports everything for you. That's separate. We do start from nothing, and we build as far as we can get. All right. Results. All right. We've been trying different methods for a while. It was a lecture only in print reading, but it wasn't enough. A lot of students said, this is not enough. This is not enough. We are not getting the big concepts. It seems so far, it's only been a couple years, that the hands-on examples has been the ticket. We've had students that are not necessarily the best in machining, and they grasp this, and they start, their wording changes, and they start looking at things from a fully defined standpoint, I guess you could say. We were able to remove the why are we doing this? And I'm hoping a lot of you guys understand where I'm coming from. Engineering students would just say this about like maybe differential equations. Why are we doing this? We're never going to use this. This doesn't make sense. Why, and just complain. We were pretty much able to get rid of that. Maybe we dropped it by 90%. Okay. Mostly, even if they say we don't do it at work, it's just the way it is. And they're readily, now they know how to work with it. It's not like learning a brand new thing when you already think you know, if that makes sense. They just understand it, and they learn to work with it, and it's worked out really well. The redundancy and us trying to synchronize topics is key. It's very difficult. I'm not going to say it's not. We've had some success, and sometimes it's just, this class did not advance the same as the previous year, and we had to pull. We only got 15 weeks a semester, so it does require a lot of work between multiple instructors. We have multiple sections, day and night. It can be tricky, but it does help. If they hear it twice, if they need a topic for multiple classes, they put more effort into learning it, is our experience. Now, students have entered the workforce out of our program, being able to make parts day one, and GD&T or not, didn't make a difference. They know how to work with it. One of our local companies, they were really impressed with one of our students that just graduated. He came in and nothing was, he had to learn the machine. It was more advanced machine. It's not a Haas. But he went out and he goes, yeah, I understand that. This is my interpretation. He was, and he cited, the standard, and this is what I need to see. And it worked out for him, and we were very pleased, and so were the employers. So that has been key. All right. And like I keep saying, we're updating. This is not a proven system. This is going to have to evolve just like everything else. We work constantly and work very hard to make this system better and to make sure our students get what they need to be machinists as quickly as possible. We want them making parts for their employers. If day one, if we can possible, we really strive for that. We're going to try moving our classes around as far as the order of classes and the co-requisites and prerequisite type things. See if that helps. Making sure that, they are really strict. One thing that has always burdened us was a student that's out of sequence. That student now is not getting information, and it falls apart for them, and it's very unfortunate. The other thing, our newest focus is going to be individual student accountability. So you, student A, you make this part, you made a mistake, it's your fault. It's not blaming the teammate, none of that. I want to put that in there because that's something that it was brought up by our advisory board. It was brought up every time I go out in industry. They need people who can take the part, get the raw stock, make the part, deliver part, to inspection or inspect the part correctly on their own with little help. And that's a tall order, but that seems to be the local demand for us. Questions? Now, if you want, we have a question and answer area. I know I ran a little later than I wanted to, but I'm open for questions and answers. And again, if you don't have it now, you can always shoot me an email. I can also, even an email, you give me a phone call, I can email it to you. I know a couple of people already emailed me about this. If you're out there listening, I will forward the drawings, a couple of drawings I just forgot recently. So if you have any questions, go ahead and put them in the Q&A. Questions or comments. I'm curious to see what everybody else is doing, to be honest. We're the only school in the area, college at least, that really does this. Not the GD&T, but the machining in general. So besides HTEC, we don't, you're our main contact. So if you have any questions, let me know. Okay, a couple of these. Yep, that's good. Yeah, Sean Burns. The other one was ITD machinist. Thanks, Randy. Hi, Sam. Yeah, that was the second time I saw that question about the YouTube channel, so bear with me here. So you have YouTube channel for ITD machinist. That's mine. And the other one is R. Dean Odell. And I'll put that in there. So I put R. Dean Odell out in the Q&A area. Textbooks. We use Bruce Wilson's textbook. I do like his textbook. I think it has more info. One of the big issues we have is true position. A lot of questions on true position. There's a lot going on. Bruce Wilson goes into great detail on that. Alex Krulikowski is also a great author. So we do use different textbooks. But Bruce Wilson is our primary one. I think we're on the 7th edition, but 6th and 7th are pretty good for our needs. Magnifying, what do we got here? Okay, magnifying a turn part. So let me get that for, who is that? Peter. This one. Okay, so here's that turn part. Okay. And we just recently added to this one, we added the ID work with the main intent of covering boring and turning in one project. Again, material costs are always an issue. So we did standardize with 2-inch round stock for most of our turning work for any general learning. If it's a specific project, we do have a couple of parts that require 3 or 4-inch aluminum and or steel, depending on what class it is. That's different. But for projects, most of the early projects bounce around with working with, for turning at least, 2-inch aluminum, 2-inch steel, 2-inch stainless, 2-inch cast iron, brass, whatever. Would a field trip to industry help to answer why doing this? Sometimes. Depends on the facility. If the facility's real big with it, yes. We have found a lot of field trips, a lot of the people you want to talk to, the machinists don't really say a lot. They'll say the general things for the tour, and a lot of times with field trips, they're looking at the machining operations. They're looking at, one of our local companies has a Grobe. They're looking at that run. Geometric tolerancing can happen, maybe if the presenter wants to do it, but it generally for us hasn't gone that route. All right. Nice. Good to hear. SUNY Delhi, another local one. Yep. Excellent. Yeah, true position and MMC. Yeah, upskilling experienced machinists. That could be a problem. And that's where I probably said it earlier. That's where the fight is. You know, they meet them on a change. They may say, well, why are we doing this? But it is what it is. I come from a job shop environment, so there is no legacy sort of mentality. These are the prints coming in. These are how they're getting quoted. We have to make them in spec, and that's how we get paid. And is what it is. But yeah, you're absolutely right. Yeah, it seems to be true position. True position is probably and it's funny that you say that because true position, I think, is simpler than profile of a surface can be. But profile doesn't get, either people are ignoring it or I don't know. I think it's less common in separate industries. But true position is definitely one of the most talked about and lecture intensive, topics that we cover. Do we use metric? Not currently, but that is one of the updates we're making for either this semester or next semester. They're going to bounce back and forth, and they're going to have to work with different it's metric or standard. Work with it. Let's see here. Okay. We have not worked with NIMS a lot yet. That could be on the radar. Could happen. We would probably commit to more than just the GD&T inspector test. One thing that was talked about is maybe having our students, prep them for the technologist version of the ASME test. That would be interesting. But some certifications are in our future for multiple topics, whether it's Mastercam or whatever, and whether it's NIMS or whatever system we choose. That is definitely on. That would being certified in geometric tolerancing is going to be something. We just want to make sure if they could pass a technologist test out of here, getting the ASME one would be excellent. Yep. So there's somebody else. So Brian Foster says he takes students right into the machining lab after the lecture, demonstrate how to fixture inspect what he was just going over. That's huge. That's the same thing we've been doing. They have to see it. The pictures don't do it justice. And there's no on the board examples that hit at home like being on the shop floor, especially again with our students. They are hands-on learners 99% of the time, at least for Hudson Valley. Okay, Mike Fitzpatrick. Yes, I will send that to you. Did I miss anybody? Because we're running short on time. So I'll make sure I get all your questions as much as I possibly can. I think we're good with that. Excellent. Awesome. Well, thanks, everybody. Thanks for the questions. It was nice to see other people with the hands-on learning. Again, I'm always willing to talk about this. One of the few people that enjoys talking about geometric tolerancing. So if you have any questions or input or what you're doing, I'm really anxious to see. It's everywhere out there. All right. Our students need to know it. Thanks, everybody. Hope you enjoy the rest of your day.